Welcome back, everyone. So what we want to talk about in this sub-lecture is the galactic disk, which is the most recognizable part of galaxies. When we think of beautiful images of galaxies, really mainly what we're thinking about are galactic disks, spiral galaxies, essentially. So let's go into this in a little bit more detail. So the galactic disk is a flattened distribution of stars. It's a disk. The radius is about 25 kiloparsecs, 25,000 parsecs, and has a height of about 300 parsecs. So it's really quite thin. There's more than 100 billion stars in the galaxy, in the disk. Most of the stars in the galaxy are actually in the disk. 100 billion stars. That's really a remarkable number when you think also about how many of those stars may have planets. As we've seen that most stars it now seems like have planets. So that's a lot of possibilities for life out there. Now the thing about the disk is that we find that the metallicity in the disk decreases from the center outward. And that has led some people to think about galactic habitable zones, because you need metals in order to form planets and to form life. So there may only be a small part of a small range of radii from the center where you could actually form planets and form life. The rotational period, the whole disk is rotating, and the rotational period around the sun is around 233 million years. It takes about 200 million years to make one orbit around the center of the galaxy at the location of the Earth. Now, any individual star is both orbiting the center of the galaxy, but it's also, because of interactions with other stars and clouds, also going up and down as well. So there's both the roundy round motion, there's an orbital motion, and there's a vertical oscillation up and down through the disk. And that's one way we can actually also tell about the age of stars, because the older a star is, the more time it's had to interact, and the larger its excursion up and down through the plane of the disk we expect. Now, we have in our own galaxy evidence for spiral arms. We believe we have spiral arms in our disk. It's difficult to tell, though. It's very hard to make these measurements from inside the galaxy. It's much easier to look at external galaxies and see they have spiral arms. And the way we've done this, essentially, is first of all, we've looked for things like hot young stars. Because we know that stars form in molecular clouds. The spiral arms are themselves built out of molecular clouds. They're regions of high densities of gas as well as higher densities of stars as well. And since we know that young stars, O stars and B stars, massive stars, don't last very long, 10 million years or so, we know that those stars really are pretty much going to die where they're born. So we can use, if we map out the locations of O stars and B stars, we see that they actually do exist in a spiral-like pattern. We also see some evidence in different kinds of gas. If we're using radio waves, we can also make measurements of the galaxy, and we see evidence there as well for the existence of spiral arms. So we definitely have some idea that there are spiral arms in our own galaxy. And now the next question becomes, why are there spiral arms? Why are there spiral arms in our galaxy? Why are there spiral arms in any galaxy? So let's think a little bit about spiral arms. Now, people, when they first see those spiral arms, they think like, oh, this is just, this is material that's being wound up. The galaxy is rotating and material is being wound up. And you can sort of think of that as if, like this string and this stick here, if I were to wind the stick up, I would get a nice spiral pattern wrapping around the stick. But as you can see, the spiral pattern is going to be quite tight on the stick. If I'm actually taking material and winding it around, what I would expect to see after 10 rotations of the galaxy, I would expect to see 10 turns, 10 spiral arms. And it turns out we don't see that. We don't see that many we don't see such tightly wound spiral arms. So that tells us that the spiral arms in galaxies can't be just matter being wound around the center. There must be something else going on. And what astronomers and astrophysicists discovered after years of study was that any rotating gaseous system would support waves, spiral waves moving through them. So for example, the waves, the sound waves that you hear when someone is talking to you is not made up of atoms coming from your throat and actually traveling to the other person's ear. They're just waves of compression that move from one set of atoms to the next set of atoms. So it's a pattern that moves through matter rather than the matter itself moving. And for a rotating gaseous system, spiral waves are a natural consequence of just any kind of perturbation. So if you take a rotating system and shake it a little, you're going to naturally form these spiral waves. And what the spiral waves do, just like sound waves, is they compress gas. And as the wave sweeps around the galaxy, the gaseous disk in the galaxy, it compresses the material. And because it compresses, that's why you can get star formation occurring. That's why you see star formation happening preferentially in the spiral arms, because that's where gas is being compressed. And once it's compressed, gravity can take hold of that material and collapse that gas and allow it to form stars. The stars themselves, as the spiral wave sweeps through, will also be compressed, so you'll get more stars more closely packed together. So the spiral arms are made of both gas and dust. So it turns out that it's a very important thing to recognize when you see these beautiful pictures of spiral galaxies, that those spiral patterns are actually just a form of sound wave in some sense, a form of compression wave that is traveling through the disk. Okay, so that tells us about the disk. Now let's move on to study another structure in the galaxy.